Hiya, everyone. It's an honor to be here to have this talk, Breaking Retrieval Augmented Generation Barriers, RAGFlow's Technical Breakthroughs, and the Infinity's AI-native design. I'm Yongteng Lei, a recent graduate from University of Edinburgh, and now I'm working at InfiniFlow, a startup focused on AI infrastructures. We have two main products. One of them is Infinity, a high-performance AI native vector database, and the RAGFlow, an open-source end-to-end RAG solution for enterprises. Interestingly, RAGFlow was open sourced at the April Fool's Day of 2024. And I don't know if it is intentional, but over the past 2 months, I've been working on the RAGFlow's core features, and I've witnessed how it captured global attentions and reveals the potential of its design in real-world enterprise use. So that's exactly what I want to share with you today. So let's get started. This is the roadmap for today. First, I will briefly introduce the traditional RAG process and highlight the challenges that a naive approach might face. And then I will present the big picture of how RAGFlow is designed to tackle these challenges. Next, we will dive into three core aspects of RAG, let's say chunking, retrieving, and agentic thinking, and we will explore practical implementations and design philosophies introduced by InfiniFlow. Finally, I will wrap up and finish this talk and hope you enjoy it. Okay, this is a classical naive retrieval augmented generation process. It operates in two main phases. First, we extract and index knowledge. Documents are split into chunks, converted into embeddings by an embedding model, and stored in a vector database. And then comes retrieval and generation. When a question is asked, we retrieve the most relevant chunks using the query's embedding and feed them into a large language model to generate a grounded response. And this is why RAG is often called the external memory of large language models. It allows the model to go beyond outdated or incomplete training data and instead ground its responses in refresh, reliable, and even private internal information. Okay. In fact, the traditional RAG pipeline works fine for plain and clean text data, but when it comes to complex data like scanned documents or files containing intricate tables and figures, it becomes hard to recognize and extract meaningful information. This can result in poor vector representations, and automatically we call that garbage in and garbage out. Second challenge is low hit rate. A classic pure vector array can only represent approximately semantics. Either a token or a document can be converted a single embedding, let's say vector, and thus vectors are not perfectly enough for precise retrieval. But it is essential for enterprise RAG. Therefore, poor vector store can lead to low hit rate. Third, there is often a semantic gap. For example, here is a query like Apple's impact on the ecosystem. This could refer to agricultural or technical context. And pure vector retrieval cannot disambiguate that very well. So moreover, tasks like query focused summarization or multi-hop question answering highly rely on the contextual understanding, reviewed in the limits of shallow similarity-based retrieval. Okay, this is the architecture of RAGFlow. We could see that RAGFlow really did a lot of things to tackle the challenges we mentioned earlier. Um, to ensure the quality of pre-processed data, we developed a series of models called DeepDoc, which refers to Deep Document Understanding. It has two parts. The first part, neural networks to detect documents, layouts, and the parsers to deal with the intricate structures within the document. It works for many forms of documents and fine-tuned for various scenarios like laws, manuals, papers, reports, as well as different kinds of different PDFs filled with tables and diagrams. And to address the semantic gap, we leverage techniques like GraphRag and Raptor as a document pre-processed pipeline to adopt large language models to better align them with users' intent. After the pre-processed stage, we've come to the final pipeline, which is to address the low hit rate issue. We have a state-of-art um, AI native database, which is dedicated design for RAG Infinity, providing most powerful hybrid search with fused ranking, including full text, vectors, sparse vectors, and even tensors. This hybrid search design significantly boosts hit rate, which is a must-have for enterprise RAG. Building a basic RAG pipeline isn't that much hard, and in most cases just work, but a truly valuable enterprise-grade RAG solution is much more than that. It requires thoughtful design, solid engineering, and that is what Infinity Flow is all about. Okay. Here is a benchmark from one of our clients. The data is just data, but it seems clear that RAGFlow just outperforms traditional or other RAG solutions, at least to some extent. Let's go to chunking. The core secret of RAGFlow is deep doc, as mentioned earlier. We perform document layout detection first and use different pipeline to uh, handle the content based on the document type. If it is normal type, normal text, we check if it is scanned file. If so, we perform actual OCR talks here and then chunking it. If it is an image, we crop it and then investigate it carefully and then apply the structure parser to it. We could use an external vision language model to enrich the content if possible. And for tables, RAGFlow trains a dedicated model to tackle intricate and complex tabular data, which is the key focus and one of the most important features prized by our users and clients. This is an example post result. I do think this is the most impressive feature of RAGFlow when I first look at it. It's just amazing. I mean, we can not only say where the chunks are located in the original document, but also can edit their content if the recognition is not satisfactory enough. But this task could be surprisingly challenging for sometimes, because we need to map each cell with its corresponding table header so that we can learn the semantic meaning of it. Also, we need to handle multi-table header, where a single header here might contain multiple indicators. That's this. And sometimes table may lack clear visual boundaries with the cell, and this can sometimes confuse the detection model like this. And here we also encounter more merged cells that span across rows and columns. Okay. What makes it worse is that sometimes the table can be split across pages, breaking their continuity. Okay, to address this, we basically have two options to go. One is using CNNs, where we treat it like a detection task. The downside of CNNs is they don't generalize very well. And the other way is use generative AI. The idea is um, if we have a codebook that can generate tables just similar to the originals, then we consider this codebook is a good representations. And based on that, we can train a transformer, encoder, and decoder to parse the tables. This method generalizes better, but is expensive and heavy on computations. Our tests shows that it can take about 1 minute to pass just 1,000 tokens, so it's super expensive. And so in the end, we embrace the DNNs where generative AI can sometimes more accurate, but DNNs give us a good balance between accuracy and speed. Yes. However, we believe that the future belongs to a dedicated vision language model can handle this task independently. And this is the direction we are actively pursuing. Yeah. Just like I said, RAGFlow works like a multi-modal RAG. We can say two approaches here are highlighted. They are related to tensors. We will see it shortly. Yeah. Let's step into retrieval. RAGFlow relies on Infinity, which is a self-development and AI native database, providing powerful hybrid search with fused ranking. It supports multiple types of index, especially for tensor and full text. And users can choose any combinations to perform the hybrid search without sacrificing the performance. It's called AI native because it's dedicated designed for RAG from the scratch. Yeah. Based on our benchmark, Infinity seems blazing fast and efficient. Here, let me highlight the value of hybrid search. NDCG, which is normalized discounted cumulative gain, is a metric that evaluates the quality of retrieved documents with higher scores, which means indicating the better quality. This diagram, BM25 refers to full text search, and dense for dense vector search, and so on. We could say that the two-way recall performs better than single-way in terms of NDCG, where three-way recall here performs the best. This perfect line with the funding of the funding published by IBM Blended RAG, which published in April 2024. We can use Infinity to reproduce their funding. Besides, we found that the results can be even much higher if we change the naive fuse ranker from RRF to Kubert reranker, which is actually a tensor-based reranker. We will see it shortly. Yes, we could see that we got overall improvement by simply use the Kubert as a reranker. Yeah. Here we have some classical re-ranking model architectures. The dog encoder here is actually how vector search works. The query and documents are encoded separately. However, only a single embedding is got as an output, which is used to compute the similarity during the online retrieval. This brings two shortcomings. First, it brings semantic loss. Definitely, a document just represented by a single vector. And second, it cannot capture the semantic interaction between query tokens and document tokens as other ones did. Okay. For the cross-encoder architecture, it's just how general reranker works. Both the query and document are processed together within the transformer encoder. Therefore, it can fully capture the semantic interaction between query and document. However, it requires the model inference during the online retrieval. It's super time consuming, and that is why this can only be used as a reranker. With the challenges posed by the previous two architectures, Cobalt comes to play, which is the earliest, the late interaction encoder. Cobalt just performs most computation during the offline stage. It store all embeddings for each token during the indexing stage. It means that each document is represented with tensor instead of a single embedding. That is why we introduced tensor as one of our data types. Okay. During the online retrieval stage, only the query is required to be encoded into a tensor, whereas the left computation is just to accumulate the pairwise similarities among each query document embedding pair. So this, which is much cheaper than the way of cross encoder. Therefore, I think the late interaction model is very attractive of RAG. What's more, a deeper investigation by us shows that Cobalt just performs both equally well as a ranker and a re-ranker, but it's much cheaper and faster as a re-ranker. So this will bring us another remarkable benefit. Traditionally, um, a cross encoder is used as a ranker to select the top 10 result for the given question due to the performance limitation. But however, with the Cobalt ranker, we can now perform re-ranking directly within the infinity, and which is significantly more costly effective, approximately 2 orders of magnitude more efficient than the cross encoder approach. This is even eliminates the needs for GPUs during online retrieval. Okay. So moreover, tensor ranking also allows us to re-rank a much larger candidate set. Let's say top 100 and or even top 1000 result. This means that even if the initial retrieval isn't highly accurate, we still have a strong opportunity to salvage it in the ranking stage. Not only that, the late interaction model, let's say Copilot, could greatly enhance the capability of RAGFlow to work as a multi-modal RAG. To process a PDF file with figures, we can present each page image of PDF as many visual patches here, and each patch is then converted into a high-dimensional dense vector generated by Copilot. Therefore, we can use a tensor to represent each PDF page or image. Does that make sense? This is how it works. We pre-process the PDF with Copilot and stores the tensors into Infinity database offline. And during the online retrieval, transform the question into the tensor user Copilot as well and find the images that may contain the answer, and then send these images to a visual language model to give the final answer. Although tensors are powerful, but they are hard thing in real-world products. Why? This is mainly because that they come with heavy storage overhead, and managing them at scale is difficult. So if we want to go further, there are two angles worth looking at. Depending on the task, can we selectively apply binary quantization here on the infrastructure side? Or can we use models like MRL or Constable to get better semantic understanding with less computation? Okay, definitely worth a try, right? Okay. So the last topic, agentic. Agentic sounds really sexy, isn't it? If the last year was if the last year um, was a year of RAG, I would say this year belongs to agents. Agents is the game changer, really. It shifts the paradigm from the simple two-step interaction where people just ask questions and the large language model gives the answers to a multi reasoning process. And agentic RAG takes things even further. For now, people may ask a vague question. Large language model start thinking, planning, reasoning, and splitting the question into multiple sub-questions. Instead of retrieving once, this this process may iterate many rounds, or maybe invoke other agents or models if necessary to give the final answer. Here is an example. We are asking who has more sons, Elon Musk or Trump. Large language models start to generate the chain of thoughts and gathering information for each sub-questions, and finally gives the final answer by synthesizing the information retrieved from the internal knowledge base. By the way, in this example, we got the thinking output even without reasoning model, like a DeepSeek R1. Yeah. So agentic RAG actually reveals a core insight, which is memory is essential. But what does memory truly means for a large language model? I think it's simple. It's just about enabling reasoning over an infinite contact. That's exactly what we are building in RAGFlow, and we do it in two key ways. First one is filtering, and we're helping the model focus on what truly matters. And the second one is fitting. We're supplying it with reasoning-ready data, such as structured sequences from GraphRag or Raptor or other frameworks. RAG isn't just about retrieval anymore, it's the foundation for true agent memory. Okay, so the question is agent memory the same as RAG? Not exactly, but they are related, but not the same. Yeah. Agent memory comes in two forms. Short-term memory, which stores session level info, and long-term memory, which is often powered by RAG. But agent memory needs more than just the retrieval, right? It needs real-time search, like short-term memory, and it need to handle time. What is recent, what is outdated, and what is old. And moreover, it need to learn to forget so it can stay focused. That's where RAGFlow comes in. It aims to be the agent memory layer for all agents. We're still keeping its own agent framework. Okay, time flies and the time is late. To wrap up, I would say RAG is not large language model operations or orchestrations. It is the essential database of the large language model era. Okay. Okay, this is the end, and thanks for your attending and listening. If you are interested in learning more about us, just feel free to reach out. And thank you.